In this video, we will discuss the classical free electron theory of the metals. In year 1900, Drude presented a model for the metals, and in this model he assumed that the valence electron are assumed to behave like a gas with positive ions constituting the core of a metal, and these electrons, for example, we have this metal I have drawn like this, and there are free electrons. They assume that these electrons as like a gas, and these electrons are confined to move within the metal because these electrons, they carry the negative charge, and the core, positive ion core, it carry the positive charge. So due to the electrostatic attraction between these electrons and these positive ions, they remain within the metal. So in 1909, Lorentz proposed that the free electrons in the metal obey the Maxwell-Boltzmann statistics. So the combination of salient points of both Drude and Lorentz constitute the classical Drude-Lorentz theory. So these two, Drude and Lorentz, they propose the classical free electron theory for metal using some important assumptions. And what are those assumptions that I will listing here now? The first, they assume that metal structure consists of positive ion cores. These are positive ion cores with the valence electron moving freely. Moving freely among these ion cores. mean to say that they will not remain at move around any single, but they move around the this metal, within the metal. And second assumption was that regarding the behavior of these free electrons, they said that the behavior of free electrons which are moving inside the metal is similar to that of atoms or molecules in a perfect gas, that they move like in the gas, they move this zigzag motion, you can say. When there is no, we are not applying any external field to these electrons, they move in zigzag fashion like that. And the third thing, they consider that the mutual repulsion among the free electron is ignored. They haven't considered their mutual attraction, because the electron they carry the negative charge, but the mutual repulsion is ignored in this case. And fourth point, they have considered that free electrons are negatively charged. Free electrons are negatively charged particles, while the atoms or molecules of a perfect gas are mostly neutral. Because in the case of, because we are comparing with the atoms and molecules, so in the generally in gases mostly they are neutral, but in this case we have, considering they are equivalent to the like the gas, but here these free electrons they carry the charge. And fifth point, that these free electrons obey the Pauli's exclusion principle. And another point, these free electrons experience constant and uniform electrostatic field. Due to the iron core, due to iron cores, because here we have considered. So these free electrons, they experience the constant or uniform electrostatic field due to these positive ions. And another point, for example 7, that total energy of these free electrons inside the metal is almost equal to their kinetic energy. And because here we are considering that positive and negative, these electrons, they are carry the negative charge and iron core carry the positive charge, so the whole system is electrically neutral. So we can write here that at its point that total negative charge of electrons must be equal to the positive charge of iron cores, and hence that metal is, hence you can say metal is electrically neutral. And another point we can consider here, the 9th, that because now this negative charge electrons, they carry negative charge, and these iron cores, they carry the positive charge. So the electrostatic attraction between these free electrons and iron core is responsible for holding the electrons within the surface of the metal. So we can write here 9th point, that the electrostatic attraction between free electrons and iron cores is responsible for holding the electrons within the surface of metal. Okay, and these free electrons always Maxwell Boltzmann statistics under equilibrium condition. And another point, we can write that movement of these free electrons inside the metal is equivalent to the as we know that we are considering the potential well problem in quantum mechanics. So here the movement of these free electron is equivalent to like this. This is well, potential well. Okay, and this is, we have metal surface. This is representing metal surface. And this is, we have, for example, electron, and this is the potential V naught, and here we have like this represent the vacuum. So this, in this case, the movement of free electrons inside the metal is equivalent to the motion of free electron in a potential well. So this is just like potential well problem. So free electron, they behave like in this problem. Okay, so now, so these were the assumptions important assumptions of Drude and Lorentz. They have proposed for discussing the formalism of classical free electron theory of the metals. Now we will try the expression for electrical conductivity using this Drude theory. Electrical conductivity. So in this theory, we will drive the expression for the DC electrical conductivity. Okay, DC electrical conductivity. So now that, for example, this is a metal, and if we apply the electric field in this direction to this, so these electrons within these free electron, they will move in this direction or drift in this direction. So under the influence of applied electric field E, the electrons, they will get accelerated. So the expression for the acceleration of an electron under the influence of an applied field E can be written as, so we can write this F m E, mass of electron, A is the acceleration, this is equal to minus E is the charge on the electron, E is the electric field. So from here we got the expression for the acceleration. So this is E by m into E, and here me is the mass of electron, and E, this represent electronic charge. Now we can write because this is the electron, it is drifting in this direction, so we can represent its denote the drift velocity with this symbol Vd. Okay, so this mean drift velocity we will write in term of the relaxation time. So first if we define this tau is representing the relaxation time. So how we define this relaxation time? Relaxation time is a measure of time required to relax an electron when the external applied field is removed. Okay, so this will define the relaxation time, or I can also denote it with that this relaxation of the electron after the removal of electric field. So say here we have time and say this is the Vd drift velocity, or you can say that this is the average drift velocity. So what will happen that it will not become zero immediately, but like this, slowly and this approaches to zero, or it may behave like this. So here now I have represented two curves. In this is curve number 1, this is curve number 2. So in the curve number 2 we can say the value of tau is large in this case because it will take more time, whereas in this case 2 the tau is, in case 2 tau is small. So in this way the electron they are relaxing after the removal of external field, or we can say that electrons are relaxation of the electron to the equilibrium. Okay, so the expression for the drift velocity we can write here that this is mean drift velocity. I will write a mean drift velocity assuming the average velocity to become zero immediately after a collision, and we can write this expression like this: Vd is equal to this is acceleration. Okay, so we know that acceleration is, we can write this Vd by tau, and a from here we have this, so we can write this Vd is equal to minus e by me into tau. So say this is equation number 1, this is equation number 2. Now we will write the expression for the net current density, because when we are applying the field, the electron they are drifting in the direction, and negative sign here, this negative sign is representing that the electrons accelerated in the direction opposite to the applied field. So this negative sign, what is representing? That accelerated electron in the direction which is opposite to the applied field direction. Okay, so the net, to write the expression for the net electric current density, net electric current density, we denote this with symbol J. So we will consider here N is the number of electrons per unit volume, and these all electrons, they are moving with the constant drift velocity Vd. They are moving with the constant velocity, this Vd. So the magnitude of this current density I can write as J is equal to NE Vd, and the expression for Vd, we can use this equation 2. I write a magnitude, and this becomes NE square by ME into E. So this is expression number 4. So in this manner we got the expression for the net electric current density. And we know that according to the statement of Ohm's law, according to Ohm's law, I can write this current density J is equal to sigma into E. So if I compare this with the equation 4, if I compare with the equation 4, I can write the expression for the sigma, and sigma is equal to NE square tau by ME, and this is the expression for the electrical conductivity. Because this is J is this, so sigma, we can write this NE square by ME. Here we have left out missing, sorry, tau. So this is the expression for the conductivity. And this electrical conductivity, from this we can also get the expression for the electrical resistivity. You know that the reciprocal of, that is the reciprocal of electrical conductivity, which gives the electrical resistivity, or I can represent this electrical resistivity symbol rho. Rho is equal to 1 by sigma. Now we will write the expression of this electrical conductivity in terms of mobility. And how we define this mobility? We can define mobility defined as drift velocity per unit electric field. Okay, so I can write this and denote this mobility with the symbol mu. Okay, so mu I can write this is equal to, this is drift velocity divided by electric field. Okay, this is the mobility. So this above expression, this of electrical conductivity, I can write this is in term of sigma Ne mu. So we wrote this expression of conductivity in term of mobility. Say this is expression number 6. Say this is expression number 7. Say this is expression number 8. Okay. Now we know that according these electrons in metal, we will assume the electrons in a metal to obey the kinetic theory. They obey the kinetic theory, and we can write the expression for the relaxation time in term of thermal velocity. That we write with simple Vt as this. So this expression for the relaxation time, I can write this tau is equal to, this is the thermal velocity divided with